Hello, my name is Andrew Cheek. I'm a postdoctoral researcher at the Tsingtao Lee Institute in Shanghai, China. And today I'm going to talk to you about uh, ways to test the dark origin of neutrino masses. And this is based on work I did with Luca Vestinelli and Hongyi Zhang. We got this work published in the Physical Letters Review Letters earlier this year. So we all know the standard scenario or standard kind of law is that neutrino oscillations means neutrinos have mass. And the story goes that we have neutrinos that interact in the flavor basis via the electroweak interactions that I show here, and they propagate in the mass basis like every particle does. You relate these two by this transformation matrix, unitary transformation matrix U, which is the PMNS matrix, which I graphically show here. And because this matrix has non-diagonal terms, you can have transition probabilities basically after a given time of propagation, a a neutrino in the B flavor state can transition into the alpha or a different flavor state. Now, what do oscillations actually prove? They really only prove one thing, and that's that the Hamiltonian has the form like this, the standard kind of Hamiltonian of a free particle with mass. Okay. And what it shows really is that the potential of your particles, your neutrinos, has a potential which goes like 1 over E to some constant. Recently, various works have tried to explore the possibility that dark matter neutrino interactions provide this potential. So they fake the neutrino mass behavior, they fake the oscillations from neutrino masses. And what kind of motivated me and my collaborators to look into this in more detail is the recent suggestions from DESI or from DESI data of the baryon acoustic oscillations in the early universe that basically there are suggestions there from the statistics that the sum of neutrino masses is actually negative. Um, Now, this doesn't mean that any neutrino masses are actually negative. It's more of a expression of how these neutrinos uh, affect the evolution of structure formation. Um, and another reason why I think this possibility is interesting is when the theory behind neutrino oscillations were being developed, the case for dark matter wasn't quite as strong as it is now. Okay, we know now that dark matter should be there on cosmic scales, cluster scales, and galactic scales. Perhaps that was the galactic scales was the only one that was really on solid ground in the mid 70s. So really, it is possible that you can think of neutrinos not, especially in a local environment, not traveling in a vacuum, but really in a medium of dark matter. So in medium effects have been studied for neutrino propagation since very early. We had basically in the 70s, late 70s and the 80s, the development um, of neutrino oscillations in matter, where the coherent forward scattering between neutrinos and the particles in the medium, i.e., electrons and neutrons and protons, provide a matter potential. Uh, a, a matter potential for these neutrinos as they oscillate, as they propagate. This potential can alter the effective mixing between states. And actually, it was shown in the mid 80s that the a variant density like that of the sun can enable resonant transitions, as you see, as I've shown from these Ginty and Kim plots here. So you start off, at some as you move from a very dense region to a lower dense region, you can start off in with a transition between states here. Now, could there be some similarities between this kind of coherent scattering with stellar material and other dense kind of standard model material and dark matter, which is all around us. Now, if you look at uh, the measurements for the local dark matter density, we see quite a big spread, but a converging agreement that the dark matter density should be around. A GeV like zero point 0.5, zero point 0.4 GeV per centimeter cubed. And if I basically take some EV scale dark matter from this, um, and I determine the number density of these dark matter particles, so I get 10 to the 8 per centimeter cubed. Okay, so this is almost 20 orders of magnitude smaller than the number density of particles in this of electrons in the sun, which provide this um, noticeable matter potential for transition rates. So, in order to have coherent scattering of dark matter be the source of of neutrino masses, we need to have either very, very strong couplings or an even smaller dark matter mass. Okay. So strong couplings face strong constraints. So we look at the possibility that dark matter is much lighter. Now, the reason why I chose 1 eV is because around this scale, dark matter is considered to be on the threshold of when it starts to behave less like a particle and more like a classical wave. Now, this is due to the fact that if you calculate the uh, the the number of the state occupation number in a de Broglie wavelength, basically, or the number density in the de Broglie wavelength, which is a state occupation number, using kind of the values for the local dark matter energy density and the velocity, as inferred from velocity dispersion relationship, or from Maxwellian of the dark matter profile, you can get this relation here where you see that in order for this number, this occupation number to be very large, you need to have a uh, scalar field with a mass which is much less than around 40 EV or an EV. Now, why is this important? When you have a large average state occupation number, you can describe the scalar field as a coherent state. And the solution to a coherent state is basically that of a classical wave equation. And the dark matter can now be modeled as a background field because in a coherent state, if you apply an annihilation or a creation operator to this state, it doesn't change it. And and then so in this case, we can have coherent interactions with a background field that imbue neutrinos with a mass. Okay, so here I've just kind of schematically written down that, okay, so the mass of a particle will have to be related to some coupling of that part of the particle to that background field. Okay, if I do this and I take the scalar, the classical wave like dark matter for the solution to the field here, I can get this equation. And what I see is that in order to have a sub-EV neutrino mass, I'd need to have basically very small couplings and very small masses of the scalar field in order to in the local dark matter density, right? If we assume local dark matter density, we know from supernova cooling constraints that the coupling should be very low, much lower than around 10 to the minus 7. So that means that the scalar field should have a mass which is lower than around 10 to the minus 9 eV. From this, from the uh, solution to the wave equation for the scalar field, I can also calculate the square mass difference of these fermions or these neutrinos, and we see here also that they depend on, or they vary with time. They have an oscillation. They have a periodicity. This periodicity is around 6 hours for a 10 to the minus 19 EV mass dark matter mass, and these variations basically, or this period gets shorter for for larger for um, larger dark matter masses, and these are much shorter than what oscillation experiments, the timescale of such oscillation experiments. For example, Juno recently had incredibly impressive results, but it took around 60 to 100 days to get their results. This means that we have to do some time averaging over the background oscillation of these square mass differences. And if you look back at the standard solution for the vacuum case, I have this oscillation probability going from alpha to beta, and it's some function that depends on the PM&S matrix, these U's here, and these two functions Fij and Gij. Fij is the sine squared of this mass squared difference with the baseline L, or how far the neutrino traveled, and its energy, and Gij is just the sine of the two of that angle. Now, if I replace um, the the vacuum mass square differences with the time variant mass square difference, then and perform a time average, this survival probability, or this probability function, just changes only insofar as the f and the g change. Okay, so now I have a time averaged f and g, and these include now a spherical or a Bessel function. Okay, that affect the sinusoidal or the trigonometric functions. With this, I can confront the dark origin of the neutrino masses with short baseline or medium baseline reactor experiments such as Diabay and Reno. Both experiments are dominated by the parameters theta 1 3 and delta M3 2 squared or M3 1 squared, depending on the ordering. We take normal ordering. And what we do is we basically perform a two-dimensional parameter fit to see if we can get a consistent result for both experiments. And we can. Okay, so the you can see here in dotted line here, orange dotted line, I fit new parameters. I fit the parameters for the dark neutrino masses, and we can fit the data pretty well. And statistically, they are equivalent. They're within 1 sigma of each other between the vacuum neutrino masses and also the dark neutrino masses. Okay, so that's fine. First test survived, but then we look at long baseline experiments such as a CAMLAN detector, which looks at anti-electron neutrino survival probabilities. They have multiple reactors, and the baseline changes between 130 to 240 kilometers. And this is mostly determined by the parameters delta M2 1 squared and theta 1 2 and theta 1 3. So we do the same thing, but now we include the medium short baseline results or analysis from Reno and Diabay. We include CAMLAND. We do a 4D fit over these parameters. We also include the uh, the, the solar neutrino determination of theta 1 2, which allows us to incorporate a nuisance parameter on theta 1 2. Right? We basically take new fit to 2024 results of the theta 1 2, excluding obviously the CAMLAND fit there, and we include that as a nuisance parameter on a chi-squared, and we perform a likelihood analysis. What our results show, we've got a corner plot here of the parameters we fit for, and what we find is basically as in the dark neutrino mass hypothesis, we find two local minima, two separated local minima, which we call dark 1 and dark 2. And it looks like they fit the results quite well on the likelihood analysis or but actually when you look at the best fit points of the vacuum case versus the dark neutrino mass case, we get that the vacuum hypothesis is favored by around 4.9 preference. And here we can basically look on the data and compare the uh, anti-electron neutrino survival probability uh, depending on the different solutions we have. Okay, here it's, I think, because the data is a little bit messy, it's not, and the error bars are quite large. It's not exactly obvious that the vacuum case fits better than the dark case, but the statistics tell us that it definitely does. For example, we have a substantial dip in the vacuum case here, and you're able to match better the dip at the the lower bins here. Okay, so that was using time fluctuations or time variations in the scalar field. What about spatial fluctuations? Local variations of the dark matter density will occur at scales only longer than the de Broglie wavelength, which is given by this equation here approximately. No, during any experiment, the Earth travels through the galaxy, okay, and there's a cross in time where given by here, and basically what we're saying is if you imagine different de Broglie volumes which have constant um, density roughly because they're part of the same coherent state, or they're yeah, part of the same coherent blob, de Broglie blob, over after you've traveled past the de Broglie volume, they will have variations, random variations between de Broglie volumes, basically. And so when does this matter? This matters when our mass of our dark matter is above roughly around 10 to the minus 14 eV. Remember earlier we needed for the dark matter neutrino masses, we needed the mass of dark matter to be below 10 to the minus 9 eV. Here, so we have a range of around five orders of magnitude to play with, okay? In this region, many patches will be traversed throughout an experiment. Okay, so now we have to do a spatial average of different random distributions, random variations of the dark matter density as the Earth travels through it. This affects basically the same probability uh, function, but now we have to calculate the Fij again, but now doing a spatial averaging, okay? And we take different random distributions, like the chi-square distribution, Rayleigh distribution, and cosine distribution, to show basically that this random spatial averaging suppresses all oscillations very, very well. So this leads us to the conclusion that basically in this range where dark matter masses are above 10 to the minus 14 eV, the dark matter or the dark neutrino mass hypothesis should be excluded. Okay, so with that, I'll summarize. Neutrino masses are implied from oscillation experiments, but they're not proven. And the kind of an alternative hypothesis whereby a coherent dark matter background gives neutrinos via effective masses very appealing. But this requires your field, your dark matter, to be wave-like. What we've done in this work is we've applied the wave-like properties to test the validity of this hypothesis using only oscillation experiments. And we have two cases, basically. One where the dark matter mass is below 10 to the minus 14 eV, and we find that CAMBLAND, solar data, and the medium baseline experiments such as Reno and Daya Bay disfavor the dark origin of neutrino masses. And in the other mass region for the dark matter, when it's above 10 to the minus 14 eV, we perform a spatial averaging, and this scenario severely excludes the possibility of the dark neutrino masses. Therefore, uh, our conclusion is that ultralight dark matter is unlikely to account for neutrino masses. With that, I will thank you for your time, and I look forward to talking to you in the meeting rooms. Thanks.